Dmytro Karakuts, who is talking about ferromagnetic nanotubes, nanostripes, sorry, with, I forgot my glasses, with variable cross section.
Good evening, colleagues. Today I will tell you about controlling the domain vulnerability in ferromagnetic nanostripes with variable cross-section by cross-section tailoring. It was shown that the domain wall motion can be manipulated by tailoring geometrical parameters. Controlling the domain wall motion is a key for a perspective magnetic memory and can significantly improve spintronic devices. Traditionally, domain wall manipulation is done by either application of an external magnetic field or by spin currents. However, recent experiments confirmed the possibility of manipulation by geometric parameters, as was explained already by previous talk with by Shekhar. Recent experiments of constructing these systems that were done have showed that indeed the curvature can manipulate the domain wall motion. However, they have also shown that even slight changes in cross-sectional area can have a significant effect on the domain wall motion, and in certain cases can significantly overpower the effect of curvature, as shown here. We have already done studies on the effect on the competition between the cross-section gradient and nanostripe curvature, as seen here. And they have confirmed that indeed we can explain how the cross-sectional gradient can overpower the curvature gradient. However, the second part is to study how the cross-sectional gradient interacts with an external magnetic field. To explain the experimental results, we have constructed a model for a narrow and thin ferromagnetic nanostripe with a variable cross-section. We consider a nanostripe to be narrow and thin with its thickness and width significantly smaller than length. To describe magnetic properties of such a stripe, we use a model of a classical ferromagnet with a biaxial anisotropy. Here we have three components. First is an exchange energy, the second is an anisotropy energy, and the third one, due to the application of external magnetic field, Zim energy. For such a system, the magnetization can be simplified to a single function, which only depends on an arc length coordinate on the stripe and time. Here on the formula shown angular parameterization of such function. The magnetic energy density, as was already said, has three components. The first component is an exchange energy, shown here. The second component arises from a Dzelshinsky-Moray interaction with curvature and torsion contributing to this component. The third component is an anisotropy energy, and magnetostatic interaction in our model is simplified to be just a component in anisotropy parameters, which can be done for a system with a constant aspect ratio between width and thickness. And the last parameter is Zeeman energy. In this model, we have several big assumptions. First of all, as we already said, the transverse parameters should be smaller, extremely small. In fact, they should be smaller than a characteristic magnetic length. In addition to that, we also assume that the changes in curvature and cross-sectional area are these gradients are not large. And once again, the aspect ratio between width and thickness should be constant. Domain wall motion in such a system can be explained can be described by a Q5 model of domain wall that was first introduced by Shevchenko and Magnetism in the 70s. As we can see here, it has two parameters. First of all, is Q and phi are the position and phase of a domain wall, with delta being the domain wall width. Here, theta and phi are the angles of the previously shown angular parameterization of magnetization. Using this model, we have studied two specific systems with variations in cross-sectional area. First of all, it's a nanostripe with localized constriction. And second system that will be shown is a nanostripe, wedge-shaped nanostripe. Let us start with localized constriction, as we can see here, which is defined as a function that has a local reduction in cross-sectional area. To explain the behavior of magnetic wall in such a system, we consider domain wall width to be a slave variable. In addition, we use an approximation of an narrow domain wall. Although these calculations can be done without these assumptions, it's just significantly simplifies the resulting equations. In addition to that, we also in equations will be using equilibrium value for a domain wall width, shown here. By calculating domain wall energy and applying Landau-Lifshitz framework, we can derive equations of the domain wall motion shown here. As we can see here, we have three components. Two of them are include an external magnetic field, and one is determined just by a cross-sectional area gradient. By studying this equation, we can see that under certain conditions, cross-sectional area and gradient and an external magnetic field can compensate each other and create a pinning position like that is shown on the first image. We have conducted a full-scale micromagnetic simulations of such system to confirm our analytical results. And indeed, for smaller fields, we have a domain wall pinning due to equilibrium between external field and cross-section gradient. And for larger fields, we have a domain wall depinning. To find the pinning position and the depinning field, we have studied these equations of motion near the pinning position and arrived at the domain wall pinning position equation shown here. The domain wall leaves its pinning position for fields larger than the pinning field, which was derived from this term. As you can see here from micromagnetic simulations, for smaller fields, the domain wall is pinned and its velocity is zero. However, at the pinning field, the domain wall suddenly leaves its pinning position and starts rapidly moving its rapid motion. We have also calculated its asymptotic domain wall velocity after leaving its pinning position. we have studied oscillation frequency and decrement of oscillations near pin position. As you can see here, oscillation frequency has three main components. First of all, it's a combination of external magnetic field and cross-section gradient, a second derivative of cross-sectional area, and a combination between second derivative and external magnetic field. As was already mentioned, the oscillation frequency measures is similar to the results that were shown for a case where there were no field present, except in that case, those two terms with field were absent. We have also shown that the domain wall mass is affected by the cross-section variations, namely domain wall inertial mass, which is explained here. As you can see, domain wall energy has two components. First is constant, and the second one is shown to be dependent on a square of velocity. As a result, we can say the domain wall has an inertial mass, and this inertial mass for a case with changes in cross-section variations is shown here. So here we have results for no changes in cross-section, and here we have how the cross-section variations change the domain wall mass. Let us continue to a second system, namely a wedge-shaped nanostripe. As you can see here, it has a connection between two nanostripes with a wedge-shaped expansion in the middle. Here, once again, we use the same approximation for domain wall width, and once again, the narrow domain wall assumptions is not necessary. It just significantly simplifies the resulting equations. As you can see here, unlike the previous case, we have no interplay between the domain wall, the cross-section gradient, and an external magnetic field. So we have no coupling between field and cross-section gradient. Once again, we have a domain wall pinning for smaller fields on the wedge-shaped expansion, and for larger fields, domain wall leaves the expansion and starts its rapid motion. For this case, we also derived a domain wall pinning position and a pinning field, as shown here. Here we can see that unlike the previous case, oscillation frequency equations change a bit. As we can see, due to lack in coupling between the external magnetic field and cross-section gradient, in this case, we are lacking one of the components that was shown for the previous system. Now the oscillation frequency is dependent on just second derivative of cross-sectional area and coupling between field and cross-section gradient. There is no additional coupling between an external field and a second derivative. For this case, we can also derive an inertial domain wall mass, and unlike the previous case where the constriction was reducing the domain wall mass, in this case we can see that the expansion of the cross-sectional area actually increases the domain wall mass, which can also explain the opposition to domain wall motion on a wedge-shaped expansion. So, in conclusion, the cross-section gradient creates an external driving force, which under certain conditions can counteract the external magnetic field and create a new pinning position. Near this pinning position, for a small deviations due to an small external magnetic fields, we arrive at oscillations near a pinning position. The oscillations for a case with localized constriction and wave-shaped nanostripe differ due to lacking a coupling between a cross-sectional area, a second derivative of cross-sectional area, and external magnetic field in the case of a wave-shaped expansion. For sufficiently large values of external field, in both cases, we get a domain Wall opinion from its spin position, and afterwards a motion with a high velocity. And finally, the cross-section variations in both cases modifies the inertial domain Wall mass. However, for the case with localized constrictions, domain Wall mass is reduced in the constriction, while for the case of a wave-shaped expansion, as shown here, domain wall is increased by an increase in cross-sectional area. Thank you for your attention. Any questions?
So, any questions from the audience here first? Yeah.
For me, it's a sort of evidence that if the main wall has some positive energies, and it tends to minimize its energy and it decreases its size. But another question is the value of this effect. And I don't know the question to which to compare it into, but maybe technologically, it would be interesting, maybe the question whether it's possible to create a diet on this basis. Yeah, the diet for spintronics.
Well, actually, the wave-shaped nanostripe is effectively this diet, because in one direction we have, as I have shown, domain wall pin. So the domain wall for at least small, relatively small fields, as you can see, to the half of Walker field, cannot move through this expansion. While if the domain wall moves in another, pushed in another direction, it can move freely. So this is effectively a domain wall diet.
Yeah, I understand. I mean that it is interesting to have some value to understand whether how it's effective really, or whether it's a perspective or not. Yeah, okay, thank you. I understand.
Other questions from the audience? Someone has questions online? No? Okay, then let's thanks.